Swayam Prabha. Digital India. Educated India.
Hello everybody. Today it is my second lecture of the module 11. In the module 11 I was discussing the membrane theory of cylindrical shell. In the last class I derived the general equations for the equilibrium of cylindrical shell, and today I will go for the analysis of cylindrical shell subjected to vertical loading, that is self weight along the surface of the shell and also the snow load along the projected area. So, today our discussion will be on the derivation of the expression of the cylindric membrane stresses for cylindrical shell roof subjected to self weight and snow load, and we will be incorporating the different types of directrices in the expression. So, a general expression is targeted to find out the stresses, membrane stresses in the cylindrical shell roof, and with the help of the general expression we can apply this formulation to any type of directrices, because cylindrical shell, this is actually formed when the straight line generator moves over a directrice, that is the plane curve. So, the different types of directrices are possible, and we will see the some common type of directrices for the analysis of cylindrical shell. Okay. Now, the equations of equilibrium in three directions have been obtained in the last class, and these equations are in this form. The first two are the differential equations relating the membrane forces in the longitudinal direction, that is n x and n theta x, with the component of the load along the longitudinal direction. The second equation is the equation of equilibrium in the y direction. Y direction is the direction along the tangent to the directrix. So, this second equation connects the membrane force n theta and n x theta and the load in the y direction. Third equation you can see, it is an algebraic equation and it is directly giving you the value of n theta as minus z into r. What is z? Capital Z is the component of the load along the radial direction, component of the load along the radial direction. Z is the radial direction, that is the direction directed towards the center of curvature. Okay. So, these equations need to be solved with the help of boundary conditions and given loading, then we will get we will be able to know the value of the membrane stresses, which can be used for design purpose. Okay. The equation of stresses in case of simply supported shell have been obtained in my last class also, and we have seen that for simply supported edge, means here the simply supported condition exists at the traverse. Traverse are the support at the two ends of the shell. So, the simply supported condition at the traverse, the two conditions have been imposed. One is this the n x is 0 and another is n x theta is 0. So, based on that two conditions we have obtained the constants of integration, and the final expression for n theta, n x theta and n x are given here for simply supported cylindrical shell. So, n theta is equal to minus z r, where r is the radius of curvature at any point, that is point is located by the distance x and the angle measured from the vertical axis passing through the center, and k is a constant, that k is given by 1 by r d n theta by d theta plus y. Y is the component of the load along the tangential direction to the meridian. So, with the help of this equation we can obtain the membrane stresses for cylindrical shell if the ends are simply supported. Ends are supported on traverse, and traverse may be of different form. This may be of solid diaphragm type, or it may be a tied arch, or it may be a trussed arch. So, here you are seeing it is a tied arch form. So, the condition here is that n x is 0 and x theta is 0. Origin is taken at the center of the shell. So, if origin is here, then boundary condition is specified at x is equal to plus L by 2 and minus L by 2. L is the length of the shell or span of the shell. Okay. Component of the load along three principal directions are given as x equal to 0. Capital X is the component of load is equal to 0. Capital Y is the component of the load along the this tangential direction to the directrix, that is W g sin theta, and capital Z is the component of the self weight, that is W g cos theta, if W g is the self weight acting on the shell. Okay. However, this expression will slightly alter when this snow load is considered, because snow load is assumed to act over the horizontal projected area. Okay. Let us now calculate the membrane stresses individually for stress self weight and this self weight plus live load and snow load. First we will cover the self weight plus live load, and then we will go for snow load. Okay. Now, here you can see that a arc of a portion of the shell is represented here, and the W g is the self weight acting at the point vertically downward, and its component along the radial direction is W g cos theta, and in the meridional direction it is this W g sin theta. Okay. Because this angle is theta. So, after resolving this in the radial direction, it becomes W g cos theta, and resolving in the tangential direction at this point, it becomes W g sin theta. Okay. So, the component of the loads are specified, and x is 0, the longitudinal force along the shell surface is assumed to be 0. Okay. So, these are the equations of equilibrium. From that we get step by step the different stresses. First, I shall go for obtaining n theta. So, n theta is equal to minus z r. So, n theta is directly given by minus W g cos theta, because this is the component of the load along the radial direction, that is what is z. You can see here z. So, substituting z here, and r is a function of the angle theta. So, therefore, r I have written in terms of theta, but when we consider a circular cylindrical shell, r is a constant. So, it does not vary with theta. Okay. Then we shall go for calculating n theta x, the membrane shear force. Now, you can see in my earlier slide that n x theta is equal to minus k x, where k is given by 1 by r d n theta by d theta plus capital Y. Capital Y is the component of the load along the tangent to the directrix. Okay. So, the n theta x is given by k x. Now, k is 1 by r d n theta by d theta plus y. So, this is the value of k. Now, substitute this value of n theta we already obtained minus w j cos theta r theta. So, after differentiating with respect to theta and then substituting the value of y as w j cos theta, we get this expression, and after simplification the final expression is 2 w j sin theta minus 1 by r w j cos theta d r d theta. Because here you can see when you differentiate this expression k, this n theta which is given by this, the two functions are involved here, one is cos theta and another is r theta. So, you have to differentiate, suppose if you differentiate first cos theta, then r theta will remain as it is, then secondly you differentiate r theta and cos theta will remain associated as coefficient. So, you are getting this term, therefore, d r d theta term is coming because r is a function of theta. When this r is constant for in case of circular cylindrical shell, then this term vanishes. Okay. So, after obtaining k, we now write the expression for n theta x. So, n theta x is given by 2 w j sin theta minus 1 by r w j cos theta d r d theta whole thing multiplied by x. So, you can see these quantities are dependent on theta, and this w g is constant quantity. So, at any position, at any meridional angle, the n theta x is varying with x, linearly varying with x. So, that is noted from this expression. Expression for longitudinal stress n x. So, longitudinal stress n x for simply supported shell we have obtained as this minus 1 by 2 L square by 4 minus x square into 1 by r dk by d theta. So, this expression now we will take to find out the expression for longitudinal stress. So, n x is written as minus 1 by 2 L square by 4 minus x square 1 by r dk by d theta. Now, this k is obtained as this 2 w j sin theta minus 1 by r w j cos theta d r d theta. So, dk d theta can be obtained by differentiating this expression with respect to theta. So, if I differentiate this expression with respect to theta, then I will get 2 w j cos theta minus w j I have taken as a factor because it is a constant term. Then I have to differentiate 3 terms 1 by r cos theta d r by d theta. So, these 3 terms are in the product form. So, I have to differentiate using the differentiation rule of product of functions. So, here it is differentiated, first I differentiated 1 by r. So, 1 by r when I differentiated, it becomes 1 by r square, then d r d theta will be there. So, d r d theta again combined with this, it will give d r d theta whole square, and cos theta will be here as it is. Then I will go for differentiating the other quantity. So, cos theta I differentiated, so it becomes sin theta, and then this d r d theta is there and 1 by r is there. Okay. After that, the differentiation is done on this term d r d theta, and it becomes now d square r, that is second derivative d square r d theta square, and other terms remain as it is 1 by r cos theta. So, we have got the term dk d theta. Now, it is possible to write the expression of n x. So, the expression for n x becomes 1 by 2 L square by 4 minus x square w g by r, and in the bracket whatever quantity we have got after differentiation of k, that is written here. So, the value of n x, n theta x and n theta are known in general form for the self weight. Now, depending on the directrix, the value of R and this R will change, and this will be substituted in the proper places to evaluate the value of membrane stresses. Okay. Let us see the case of snow load. Snow load for design purpose is treated as uniformly distributed load over the horizontally projected surface. So, the snow load is acting here, over the horizontally projected surface, and it is the shell surface, and we have to convert this in terms of the load that is acting along the surface of the shell, but that is done in this way. Suppose on a element the total load will remain constant. So, if I use this, say if A is the length of horizontal length of this, so P into A equal to, say this is the curve length, arc length for example. So, B into Q. So, Q becomes P into A by B. Now, from this triangle it can be seen that A by B is equal to cos theta. So, Q, that is the vertical component of the load, is nothing but P cos theta. So, therefore, this load is written as P cos theta. Now, once this load is written, because P is the intensity of the load over the horizontally projected surface. So, now it is converted to the load along the surface of the shell. So, it becomes P cos theta. So, now the component of P cos theta along the radial direction is P cos square theta, and along the tangential direction it will be P cos theta sin theta. So, three components of the loads are known now. One is x is capital X is 0 along the longitudinal axis, capital Y is P sin theta cos theta, and capital Z is P cos square theta. Then we can find out this value of k. So, n theta is directly minus z r equal to z was P cos square theta. So, we can write minus P r cos square theta. Once you obtain n theta, then you can evaluate k, and k is obtained as you see this term n theta is minus P r cos square theta. So, after differentiating this n theta with respect to theta, we get now 3 p sin theta cos theta minus 1 by r P cos square theta dr d theta. So, this term is obtained after adding y. Then the simplification is possible when you know the value of r, and if you know the r as a function of theta, again you can differentiate this quantity. For a directrix which is having constant curvature, that is radius of curvature is constant along the length of the curve, then the last quantity this dr d theta will be 0. So, this will not be existing in case of shell with constant radius of curvature like a circular cylindrical shell. Now, we have obtained a general expression for the membrane forces for the gravity load as well as snow load. Gravity load here I mean that self weight plus live load, and snow load is also a gravity load, but it is acting over the horizontally projected surface. So, we shall consider now here four kinds of directrices. One is circular, then parabolic, catenary and cycloidal directrices. The other type of directrices that are common is semi ellipse, but here I consider only 4. Semi ellipse can be treated in a different way. The 4 directrices are considered here because it is possible to express the equation of the directrix in the intrinsic form relating the radius of curvature and the angle theta. So, it can be written in this form, the equation of the directrix, a general form of equation of the directrix is r equal to r naught cos to the power n theta. So, here r naught represents the radius of curvature at the crown, that is the highest point on the shell, and n is a number which may be negative, positive depending on the nature of the curve. So, r is varying with r naught cos to the power n theta. N is a index which depends on the type of the curve, and r naught is the radius at the crown where theta is the 0, because theta is measured with respect to the vertical axis passing through the meridian. Okay. So, properties of different directrices are to be found out before finding the expression for that type of cylindrical shell. To solve the numerical problems on the cylindrical shell, we should know the properties of different directrices, and properties of directrices were expressed in the intrinsic form r is equal to r naught cos to the power n theta. So, therefore, the different curve are treated here to find out their equation in the form of r naught cos n theta. First, let us see which is a very common type of directrix, is a arc of a circle. So, circular cylinder is very common in application, and here you can see the radius of the curvature is constant at any angle theta. So, therefore, your this r is equal to r naught equal to r. So, r is constant everywhere along the circular directrix, and n is 0, because r should be equal to r naught or r, a constant quantity. So, this term should be 1. So, it is possible only when n is 0. Okay. Then we go for a parabolic directrix. Parabolic directrix are also seen in construction, because there is no hard and fast rule that for cylindrical shell the directrix should be only this circle, it can be of any form. So, we are now considering the parabolic directrix. In parabolic directrix, the equation of the parabola is to be written in the intrinsic form. So, intrinsic form is r is equal to r naught cos to the power n theta. So, see this with reference to x and y axis, the equation of the parabola is written x square equal to 4 a y, and at any point along the tangent makes an angle theta with the horizontal, and tan theta is the slope of the curve. So, if the equation of the curve is given by y, then we can find the radius of curvature at any point by the expression that is known from the calculus, r is equal to 1 plus dy by dx whole square to the power 3 by 2 divided by d square y by dx square. Okay. So, equation of the parabola in parametric form is expressed now, because to convert the equation of the curve or to find out the properties of the curve with a equation in the form of r is equal to r naught cos to the power n theta, we should express the equation of the curve in the parametric form first, then we can find the r naught and n. So, let us see this example. See, the parametric form of the equation of the parabola is written as x is equal to 280 and y is equal to 80 square, which generates the parabola that can be verified from this expression. Now, this is the parametric form of the equation. dy by dx will be t equal to tan theta, because first we differentiated y and it becomes 2 t, because if I differentiate t square it becomes 2 t dt and a is there, and when we differentiate dx, that is then it will be twice a, because differentiation of t is 1. So, twice a dt. So, now dividing this by this, we get the parameter t, which is nothing but dy dx is tan theta. Now, let us find the second derivative, because second derivative is needed for finding the radius of curvature. So, if I differentiate this quantity d by dx of dy by dx, and then we can write it dt by dx, and dt by dx from this expression can be seen dt by dx is 1 by 2a. Okay. So, r equal to, now r is found using this formula, r is equal to 1 plus dy by dx whole square power raised to the power 3 by 2 divided by d square y dx square. So, once we know dy by dx and d square y by dx square, now we can find the r. So, r is computed as twice a into 1 plus t square raised to the power 3 by 2 equal to 2a, 1 plus t is tan theta. So, 1 plus tan square theta raised to the power 3 by 2. So, now this term 1 plus tan square theta is nothing but sec square theta. So, once it is raised to the power 3 by 2, then it becomes 2a sec cube theta. So, that is nothing but, because sec theta is reciprocal of cos theta. So, we can now write 2a cos to the power minus 3 theta. So, the equation of the parabola in this form is found out. The form is this r is equal to r naught into cos to the power n theta. Okay. R naught. So, r naught for parabolic curve is twice a, and n is equal to minus 3. Okay. Now, let us go to the cycloidal directrix. A cycloid is formed by a point on the circumference of a circle as it rolls along the straight line without sliding. So, this is the definition of cycloid. Okay. The parametric form of the equation of the cycloid is x is equal to a into t minus sin t and y is equal to a into 1 minus cos t. So, these two equations are seen. Okay. So, parametric form of this cycloid is x is equal to a into t minus sin t and y is equal to a into 1 minus cos t. Okay. So, dx we can now find, dx will be a into 1 minus cos t dt. So, a into 1 minus cos t dt. dy can be found, dy will be a sin t dt. So, a sin t dt. So, dy dx is now calculated, dy by dx will be sin t divided by 1 minus cos t. Sin t can be written as 2 sin t by 2 into cos t by 2 divided by 2 sin square t by 2, because 1 minus cos t by 2 is 2 into sin square t by 2. And after simplification of this quantity, it can be written as cot t by 2. Now, let us differentiate again to find out the curvature. So, d square y by dx square is now found out. So, it is d by dx of dy by dx. So, after differentiating this quantity, one can find it that it is equal to minus half cosec square t by 2 into dt by dx, because first I have differentiated this expression with respect to t and then t is differentiated with respect to x. Okay. So, after simplification you can write cosec square t by 2 divided by 2a into 1 minus cos t. Okay. Further simplification is necessary to bring this equation in the form r is equal to r naught cos to the power n theta. Okay. So, d square y dx square now can be written as 1 by 4a cosec to the power 4 t by 2. So, now put this value of this dy dx that you have found cot t by 2 and d square y by dx square as 1 by 4a cosec to the power 4 t by 2 in this expression for radius of curvature. So, after simplification we get it is equal to radius of curvature is equal to minus 4a sin t by t. Okay. Now, you can note that the theta is equal to pi by 2 minus t by 2. So, this if I t by 2 if I substitute here as pi by 2 minus theta, then it becomes minus 4a cos theta. So, that means here now we have been able to write the expression in the intrinsic form, that is r is equal to r naught cos to the power n theta. So, now find out what is r naught. R naught here is minus 4a and n is here 1 because it is cos theta. So, n is 1. So, for cycloidal directrix, the equation of the cycloid to be used in our expression for finding the membrane stress is given by minus 4a cos theta, where r naught is minus 4a and n is 1. Okay. Next directrix is the catenary, which is also common in some application. Now, equation of the catenary can be written as y is equal to a cos hyperbolic x by a. So, dy dx is calculated, dy by dx, that is the first derivative is calculated, which is nothing but tan theta, and it is equal to sin hyperbolic x by a, because 1 by a will come out and it will be cancelled with a. So, the term remains only the sin hyperbolic x by a. Second derivative is calculated and it is equal to 1 by a cos hyperbolic x by a. So, two derivatives are found. Now, we can go for calculating the radius of curvature. So, radius of curvature is given by 1 plus dy by dx whole square raised to the power 3 by 2 divided by d square y by dx square. Substituting the value of dy by dx and d square y by dx square, now we can write this. We have already got dy by dx as sin hyperbolic x by a and d square y by dx square equal to 1 by a cos hyperbolic x by a. So, substituting these values, we now get r in the form of a cos hyperbolic square x by a. Okay. So, now it has to be again I am telling that the equation has to be brought in the form of r is equal to r naught cos to the power n theta. So, trigonometrical function cosine has to be brought here. So, to do this, we take this sec square theta equal to 1 plus tan square theta, and this tan theta we already obtained. Tan theta is your sin hyperbolic x by a. So, now substituting this tan theta as sin hyperbolic x by a, we can write sec square theta equal to 1 plus sin square hyperbolic x by a. Now, we know this trigonometrical identity, that is cos square hyperbolic x by a sin square hyperbolic x by a equal to 1. So, that means 1 plus sin hyperbolic square x by a is nothing but you can find it, it will become cos hyperbolic square x by a. So, this is written here in this form and this is nothing but sec square theta. So, now we can relate, because this is related to cos theta, sec is related to cos. So, sec square theta will be cos to the power minus 2 theta. So, therefore, the equation of the curve can be written as r is equal to a sec square theta, and therefore, r naught is equal to a, n is equal to minus 2. So, in this way we can find the equation of the directrix in this very interesting form, that is r is equal to r naught cos to the power n theta. So, that the value of r naught and n can be substituted in the general expression that we have derived for any kind of directrices. Okay. So, now we summarize the parameter of the different directrices. For circular directrix n is equal to 0, for cycloidal directrix n is equal to 1, for catenary directrix n is equal to -2, for parabolic it is -3. Okay. The equation of the curve is r theta r naught cos to the power n theta. One directrix I have not included here, because this cannot be expressed in this form, that is the semi ellipse, and that have to be found from the general procedure, that finding the radius of curvature after successive differentiation of the equation of the curve. Okay. So, let us now find the general expression for stresses under self weight. Using this relation r is equal to r naught cos to the power n theta, the radial component of the vertical load is w g cos theta, and the component along the tangential direction is w g sin theta. So, substituting this, we can now find the expression for membrane stresses one by one. First, let us find the n theta. N theta is equal to minus z r. So, w g r naught cos to the power n plus 1 theta. So, this is the expression for this n theta, and suppose it is a circular cylinder, circular cylindrical roof, then n is 0 and r is your constant quantity. So, we can find this value now. For say other type of directrices, we have found r naught as well as n. So, we can put here. Okay. So, k can be found now 1 by r d n theta by d theta plus y, that means n theta is differentiated with respect to theta, and since this is the expression for n theta, when I differentiate this, it becomes minus w g n plus 1 r naught cos to the power n theta minus sin theta, and here r is substituted as r naught cos to the power n theta, and this is the y, this is the component of the load y. Okay. So, after simplification, k becomes n plus 1 w g sin theta plus w g sin theta, which is nothing but k is equal to n plus 2 w g sin theta. So, once you find k, now you can find n theta x. So, n theta x is equal to minus k x equal to minus n plus 2 w g x sin theta. Then we come to the nx, the longitudinal membrane stress, that has to be found. The expression for longitudinal membrane stress for simply supported shell was derived as this: nx is equal to minus 1 by 2 into L square by 4 minus x square into 1 by r dk by d theta. So, if k is known as this n plus 2 w g sin theta, differentiation of this quantity with respect to theta will give you this n plus 2 w g cos theta. So, after substituting this in this expression, now we get nx is equal to minus n plus 2 divided by 2 w g L square by 4 minus x square 1 by r naught cos to the power n minus 1 theta. Okay. So, 3 membrane stresses we have evaluated. Now, we go for calculating the stresses under the snow load. So, component of the snow load along this radial direction and the circumferential direction is given as, in the radial direction it is p cos square theta, as you can see from this figure, and in the circumferential direction it is p cos theta sin theta. This is evident from figure and also discussed earlier. So, substituting this r is equal to r naught cos to the power n theta and this expression for the load component, we now first obtain n theta equal to minus z r. So, z is p cos square theta and this expression r is substituted here. So, final expression will be minus p r naught cos to the power n plus 2 theta. So, this is the expression for n theta. Okay. Now, find out this k value. K is 1 by r d n theta by d theta plus y. Y is known as p cos theta sin theta. So, we differentiated this quantity and then finally, it is found n plus 3 into p sin theta cos theta. This is of course is illustrated by step by step procedure. So, n theta is minus p r naught cos to the power n plus 2 theta, and k is 1 by r d n theta by d theta plus y, where y is p cos theta sin theta. So, it is written like that. Substituting this value of n theta means n theta is differentiated with respect to theta, we can see that this expression is obtained. This n plus 2 divided by r is now substituted as r naught cos to the power n theta, then p r naught cos to the power n plus 1 theta sin theta plus y component is this. So, after simplification it results k equal to p n plus 2 cos theta sin theta plus p cos theta sin theta. So, then taking common terms or adding this, we finally get k is equal to p n plus 3 into cos theta sin theta. So, that is written here. Okay. So, p is the intensity of the snow load. So, once you get the n x theta and dk by d theta, then other quantities can be easily found out. So, n x is nothing but minus 1 by 2 L square by 4 minus x square 1 by r dk by d theta. We have obtained k as n plus 3 p sin theta cos theta, and this can be further written as n plus t 3 divided by 2 p sin 2 theta, because sin theta cos theta is nothing but sin 2 theta divided by 2. So, it is written in this form. So, dk by d theta is nothing but n plus 3 p cos 2 theta, because 2 will get cancelled with this 2 in the denominator. So, therefore, the n x, the expression for longitudinal stress, can be written as minus n plus 3 divided by 2 r naught p into L square by 4 minus x square into cos 2 theta divided by cos to the power n theta. So, in this way we have obtained the membrane stresses, 3 component of stresses, that is n x, n theta and n x theta. For cylindrical shell having any general type of directories, here include the following type. One is circular, parabola, cycloid and this catenary. So, this type of directories are included in this expression. For other type of directrices, the general procedure should be adopted. Okay. So, after obtaining these 3 stress component for snow load and dead load, we can now find the force transmitted to the edge member. Now, you can see that shell is supported on the edge member. So, what is the force transmitted on the edge member? Because edge member will be subjected to force, that will be up to certain region it will be compressive and up to certain region it will be tensile. So, let us find out this. You can see here the n x theta. If we see the expression for membrane shear force, it is n x theta is equal to minus k x, that is x is equal to 0, membrane shear stress is 0, and it is maximum at the ends. So, one is in the negative direction and other in the positive direction. So, let us find the resultant force. So, axial force P developed in the edge beam at a distance x from the center can be given as integration of 0 to L by 2 n x theta. N x theta has to be found at this edge, that is theta is equal to theta c, theta is equal to theta c. So, at this point the n x theta has to be found out. So, it is integrated from 0 to L by 2 for the one part, and after integration this n x theta is given as minus k x equal to minus n plus 2 w g x sin theta, and let us do it for a circular cylindrical shell first. So, r is equal to r naught and n is equal to 0 for circular cylindrical shell. So, therefore, n x theta can be written as 2 w g x sin theta. Okay. So, P is now calculated as the at a distance x. So, therefore, we put the lower limit x, but if it is calculated from 0, that is center, then we put the lower limit 0. So, P is equal to minus integration x to L by 2 of the quantity n x theta evaluated at theta is equal to theta c with respect to dx. So, substituting the value of n x theta as minus 2 w g x sin theta c dx. Now, after integration we find the expression for the edge member force as w g L square by 4 minus x square sin theta c. Now, it is seen that maximum tension occurs because it is now becoming positive. So, tensile force is treated as positive. So, maximum tension occurs at x is equal to 0. So, by putting x is equal to 0, we get P max equal to w g L square sin theta c divided by 4. Okay. So, let me summarize what we have done today. In this lecture, expression for membrane stresses for cylindrical shell have been obtained for any arbitrary directrix. For some of the directrices, intrinsic equations relating the radius of curvature of the shell with the angle measured from the vertical axis can be obtained, that is r and theta is related. Therefore, the general expressions for membrane stresses under dead load and snow load were obtained using parameters r naught and angle theta. This expression can be used for 4 different types of directrices: circular, parabolic, cycloid and catenary. We will see some numerical problem in the next class. Thank you.